Honorable Vice Chair, dear participants, it's my pleasure to deliver this installation lecture today. And the title of the lecture is actually a statement, no questions, just statement. And choosing statement to be a title is a kind of risky because it immediately makes you think that I should prove you something, right? So, well, the simple proof is about 3 years ago, Steve Jobs admitted that the development of iPhone was 95% was about software design, and only 5% hardware design. From the previous two talks, you hear that, well, for mobile phones, you can develop new applications, and even you can analyze networks of mobile phones to extract some knowledge from there, which is again about computations. Like developing software is about computations, developing applications, and then even thinking of networks of mobile phones is also about computations. So it's not only 95%, but everything what follows after the development of mobile phones is also computations related. So modern engineering is computational engineering. And I can stop here and conclude the talk. Proof is done, right? But I want to take a step back and explain a little bit more how I think about it. Well, one observation is that computations was always been a big part of engineering. So every time when we refer to an engineer, we basically means that that this person has some skills to compute something, make calculations, build something. It always started from calculations. So then why modern engineering is actually computations? It always has been about computations, right? It's interesting that the translation of the title to finish is kind of change a little bit the meaning of the title. This ending, las canalista technica, it's not exactly means computational in engineering, right? It's more specific, referring to computers or just doing computations on the computers. So I basically mean something more generic on it. And let's start from a very generic thing, thinking how engineering development happens. So what we do when we develop something. In the beginning was the word. And it's true for engineers too. Engineering always starts from the existing infrastructure. In the beginning of 20th century, the steel industry was built. And that was existing infrastructure. This existing infrastructure was totally non-fit to, let's say, mobile phones, so semiconductor infrastructure which has been developed later. But that was what existed before, the existing pieces of infrastructure. Let's call them words. So the next step in engineering development, so the first step is to realize what the world you're living is in. The next is to go into details of these words, to figure out what are the laws of physics, chemistry, biology, depending on applications where you work. And this means that you find out what are the fundamental limits and what are the combinations of pieces, words, which are stable and which are in general possible. All right? Not everything is possible. It's dictated by certain laws. Well, the third part in engineering development, and it's a very important part, is basically referring to a customer. If somebody actually needs our development, the customer is always right? And then the fourth part is to actually do the development, build the things. And when we build the things, we have to always remember that a machine has a value only as it produces more than it consumes. So it has to be efficient, it has to be available for customers, it has to be secure, and could be many other requirements under the limits of the existing infrastructure. So maybe this is a good moment to make a compliment to the structure of Aalto University, because Aalto University precisely wants to combine this science, technology, and business economics in one university. And it indeed covers the whole spectrum of engineering development. Each of these steps is very, very different, and the entrepreneurship is very different from scientific and engineering work, but it's nice when it comes in one university, all the steps. So the beginning. So the beginning is basically the existing infrastructure. So we find ourselves in the existing infrastructure pretty randomly. So I mean that, well, there is a good saying that the facts are not science, as a dictionary is not literature. So if there is a steel industry infrastructure existed, it has no fit to semiconductor infrastructure, but that's what has been existed. And we find ourselves as electrical engineers, let's say working with semiconductors, in a very random world. And it's actually good things that we find ourselves in a random world. Making an analogy to what biologists has been developed in their fields. So in biology there are two processes, selection and then random choice. Selection is always pre-computed, or selection is basically selection from already existent organisms, which one wins, while random choice is something not pre-computed. It's just randomly choose whatever. And because of this random choice, you basically generating new information. So the way biologists define information is one random choice from several possible choices. In electrical engineering, we define it slightly different. We say that it's a negative logarithm of the probability of the choice. Right? So which is property of information? You can see certain analogy, but in the definition by engineers, we don't refer to the choice. What is the choice? We just refer only to the probability. Doesn't matter what is the choice. But anyway, in the beginning, when we find ourselves in a certain infrastructure and want to design something, it's random. And this randomness actually allows for generating new information, new ideas. So it's very difficult to predict in science or in technology what will be next development. Some people, futurists, are able somehow, but it's very difficult because there is a lot of randomness there. So there is no computation here. But then laws of physics come. Well, and there is quite a bit of computations, right? So we have data which we collect, and we want to build the mathematical models for this data. These mathematical models should be as precise as possible. Well, as far as the law of mathematics refer to reality, they're not certain. And as far as they're certain, they do not refer to reality. Physicists realized it a long time ago. So it's very difficult to build a very adequate mathematical model. Any model is applicable only for under certain conditions, and up to the point when physicists do not really call the law of physics any longer laws, but rather call rules. So if this satisfies, then there is a rule. For electrical engineers, and I'm an electrical engineer, so the Maxwell equation is basically where the science starts. It's a literature for us. It's no longer a vocabulary, it's literature. It's science, we can understand something there. And deriving a system of differential equations is a computation. That's where it starts. But it's a rather simple computation. You can do it only using pen and paper. You don't need computers, you don't need to analyze huge data and so on. So electromagnetic waves, in turn, is basically a signal. Signal contains data. And what we need to do with data, we need to process them to make them somehow useful. And you heard it in the previous two talks. Well, then it goes to customer. Well, signal is data with information encoded in it. And it's very difficult to define what knowledge is, right? Starting from already next step, knowledge. So we have basically data, but data is not information. Then we have information, but information is not knowledge, you know, right? It's already very difficult to define what knowledge is. So in the previous two talks, people, they tried to kind of address the question, what knowledge they want to extract and exchange, right? But it's even more. Knowledge is not understanding, and understanding is not wisdom. And whatever customer do, the final purpose is to really understand something, or at least some customers, and then wisdom is really the final purpose, whatever we do in life, right? So even knowledge has difficulty to define. The best definition I found is when you know a thing to hold that you know it, and when you do not know a thing to allow that you do not know it, this is knowledge. Confucius, 2,000 years ago or more. And to extract knowledge, you actually need to do lots of computations, very massive computations, huge networks, huge data, and this means lots of computations. So understanding and wisdom means even more computations, but machines even not capable to do it. Only we can, right? It's kind of a luxury. So it's luxury or real objective for the person. It's up to the person. Well, what can help here is basically privileged information. So privileged information may reduce the amount of computations quite significantly, and that's, in my opinion, what teaching is about. Why you come to the university. From professors, you want to hear some privileged information to make your path to understanding and knowledge shorter. Well, in engineering development, finally, what we do a design. So when we do a design, we worry about efficiency, availability, security, capacity, and so on. Well, machine, when we design it as engineers, already has a knowledge of functions it has to perform. This knowledge comes from a designer, from an engineer. So really what machine operates with is data and information, not more than that, right? So, but when it operates with data and information, so it has to be efficient. Efficiency is a big deal. And it has to operate with, let's say, large amount of data, has to have a sufficient capacity, and it should be secure, available, and so on. Well, now let's connect it to signal processing, because my field of research is signal processing. And I just want to go a little bit back in history, where it's all started from. Digital signal processing, you can say that it started in the 30s of last century, when the Nyquist-Shannon-Kotelnikov sampling theorem has been developed. So whatever we know now as mobile phone computers and so on, it basically maps the analog world to a digital world. And the enabling technique for mapping analog world to a digital world is Shannon-Nyquist theory. Oh. And then another step after this theoretical development was actually the availability of computers in the 60s. So there is a 30 years gap in between of theoretical principles development and then until it became more or less practical. And it's actually even longer gap if you think, because computers really started to be available only when Apple has been founded. Well, the discrete signal is basically binary data. So whatever signal you think of, it's the analog signal. And when we discretize this signal, we sample, quantize, and transfer it to a sequence of zeros and ones. No voltage or voltage, right? So this is basically the enabling technique. It's very nice because whatever signal, whatever phenomena we have is transferred to a sequence of zeros and ones, right? So it means that a single device, like a smartphone, can do very different operations. Can be digital camera, can be phone, of course, right? Can do computations, and can do hundreds of other operations. So in the previous eras, you might notice that different devices were actually specialized for different purposes. Nowadays, it's not a problem, and why? It's because of digital signal processing. Well, because we basically transfer all our data is just sequences of zeros and ones, the common technique or the common mathematical machinery behind of digital signal processing was geometry and linear algebra. Approximation theory too, so we basically use Fourier analysis, and from Fourier analysis we represent a signal as a vector of coefficients, Fourier coefficients, and then use the geometry and linear algebra to manipulate and describe it and develop new techniques. That was the state of the art 20 years ago. And it was a lot about computations. You know that linear algebra is really about computations, right? It's not just the closed form formula where you substituted your parameters and solved. You have to invert matrices, you have to find singular value decompositions, which are algorithms, computations, which have certain complexity and so on. The word complicated in a sense. As soon as we started to work with linear algebra, the word became more complex. And well, if nature does nothing uselessly is a question. Well, as the scientific development goes, this statement seems to be not really true because like in computer science, a very famous technique is support vector machine. When we, let's say, need to classify these black dots and blue dots one from another, and if we want to do it, we basically have to build a very complicated curve. But instead, what we can do, we can multiply our data by a certain kernel or increase the dimension of this data, and then the classification becomes very simple. We just separate one set from another by drawing a line. So we intentionally increase the complexity of the model to make the solution very simple, right? So it's not necessarily that Occam-Reiser principle is correct as in the situation when all we need is actually to extract certain knowledge. But the final objective, remember, is understanding and wisdom. So maybe, like the sayings of Einstein is still right that that basically, in order to understand something scientifically, we need a very small number of parameters. So that's what wisdom and understanding helps us to reach. Well, the previous speakers were computer scientists and electrical engineer, and here is perhaps a good point to draw a difference between one and another, right? Well, for both of us, there is no luxury when we talk about information machines, because we know that information machines can work only with data and information. But what electrical engineers do, they start designing when they know exactly the knowledge of functions which machines should perform, right? They're always connected, very much connected to physical world. We talk about electromagnetic waves, we talk about transistors, resistors, and so on. We talk about, in a very abstract way, to Fourier coefficients, and so on. But we're always very connected to physical world. The models which are much better defined than the models which computer scientists use. So the math is much more rigorous, typically, for us, which makes it simpler in a sense. But there is another difference that computer scientists aim at extracting knowledge from data on a computer. So that's why it's actually called science, right? Because science is always about extracting knowledge, extracting facts. Electrical engineers do not really extract facts. We do designs. Now, just about very briefly, if the computation power is limited or unlimited. So the computational power increases from year to year, we know it. But also the amount of data increases from year to year, even at larger scale. And then there are two design parameters when we design any computational techniques. It's basically power efficiency for what we design and production cost. Power efficiency is important because energy is limited. Production cost is important because wealth is limited. Well, wealth actually transfers to energy. It's all about energy at the end. And it has to be efficient. So we have to use deep understanding and wisdom while designing our signal processing algorithms. So what happens nowadays in the fields in which I work, so we are basically shifting from linear algebra, something which was computationally very demand, to something that is even more demand. And this is optimization in multilinear algebra. In optimization, there are few important steps in the past which happened in 1984. Karmarkar proves that linear programming can be solved in polynomial time, and then in 90s, Nesterov and Nemirovsky proved that also convex programs can be solved in polynomial time. Nowadays, we are basically working in finding polynomial time solutions for some classes of non-convex problems, and my research is actually mostly here. And what more we are up to in signal processing particularly, so we basically try to add some cognitive functions, cognition, to machines, and cooperation functions as well between machines. Examples are cognitive radio and radar, in modern technology, cooperative communication, and the tools which we use there are pretty much optimization, game theory, multivariate statistics analysis. And another field is to avoid sampling of data, but sample information right away. So it's so-called compressed sensing, a good example. And what is up there is, again, optimization, and it's all about computations. And that's what I mean that modern engineering is computational engineering. Thank you.